Yeah, so the slope fields are those little tangent lines, but like what structures are important to the, let's say if that was a population growth. It's cap? Yeah, it's cap, right? So you might think that right here, what would that be called right there? Carrying capacity. Right. And there's another interesting y value. What's another y value that would be, that happens somewhere below that? Well, yeah, you could have the initial, right? But then there's the middle, right? What's the interesting thing that happens here? What does it look like is going on where it crosses right there? Yeah, it looks like it's an inflection point. So what's going on there with regard to the population growth? So it's a point of inflection, but what else is going on? Yeah, it's the time when the rate is increasing the most. Rate increasing the most. So you might get questions like, when is the population growing the fastest? It's going to be the time it takes to get to halfway to carrying capacity. Do real life situations get played out this perfectly? No. Do they stop at that horizontal carrying capacity? No. Sometimes they go over. What happens when the population goes over? Limited resources, population goes down. So we've done this before where you've plotted solutions that start above and below the carrying capacity. It starts above, you get these curves that go down to the carrying capacity, it goes below, grows real quick, and then it starts slowing down as it approaches the carrying capacity. This is the general formula for a logistic curve. Kp times 1 minus p over L, and we'll explain what those are. So here are those things labeled. So we already labeled the carrying capacity. We have concavity changes. We have concave up, approximately exponential, and then you have different solutions. You have different solutions. Okay, so the challenge though is this. Here's the challenge, everybody. So if this is the general form for a logistic curve, what have we done when we've been given differentials? What's one thing we've done with differentials? I've given you a differential equation. What's one thing you've done that you'll certainly see on the BC calculus? Yeah. What's your overall goal? That's step one along the way to doing what? To what? Integrate. So finding a solution, right? Finding a solution. You'll have a constant, and then you have to like solve for that constant. We've done it before. So if this is the general term, what work do we do to find the analytic solution to this differential equation? Again, the definition of a differential equation is just anything that has a what in it. Any equation that has a what in it. A what? A rate of change, yeah, a slope, sure. Anything that has a rate of change in it. So in this case, it's dp dt. What's the common articulation for that? It's not labeled here, but we were calling it population change with respect to time. That's it. So if we're going to integrate this, what was that first step? You said what, Nom? You have to do what? Yeah, so this is just, okay, this is multiplication, and then going from here to here is separating variables. We have dp dt is equal to this. So what do we end up with? Well, we end up with dt over here, and dp on the left side. What do we do at this point? So we separated, and now what are we doing from there? What's that word? We are doing what? What do we want to do to get from here to here? Not differentiate. Integrate. We're looking to do some algebra right here. That's what happens here. And then we integrate. What's the thing? What happens to get from here to here? What's that tool that happens to get from there to there? Do you remember what that's called? The word is cut off. Look over to the right. Do you remember? How do you get from this to this? Partial fraction decomposition. You remember that, everybody? You have the p. You're differentiating with respect to p, but how many are there? There are two of them in two different places, so you have to separate it into two. So you separate this out, and then can you integrate? Say yes. Say yes. You certainly can. You certainly can. So you're integrating this with respect to t. So what does that become? Oh, what happened to that L? Like, what's going on here? Yeah, what cancels out? Oh, the 1 over L's on both sides. The book tends to do that sometimes. They don't explain all of their simplification. Like, what do you see on both sides? Do you see this L and do you see this L? What happens to both of those? They cancel. Why do they cancel? Those are constants with regard to this integration. We are integrating with respect to P and with respect to T. Are we integrating with respect to L? No, so they're constants, so they cancel out. And what are you left with? Oh, you're left with this nice equation. But what do you want to solve for now? What do you think you want to solve for? Keep going, keep going, keep going. What do we end up with? we end up with this right here. L over P is equal to 1 plus A e to the negative KT. Okay, so what happens here is you'll see a lot of notation-heavy stuff here. You'll see a lot of notation-heavy stuff, and instead of writing lots of constants, they group them together. So for example, what does A equal? This is really important. You see this right here? What does A equal? L minus P naught over P naught. What do you think P naught means? The initial population. What does L represent? Do you remember from the diagram I flashed by here? Remember what L represents? Carrying capacity. The carrying capacity of the population. The carrying capacity of the population. So it's notation heavy. So for a logistic function, the maximum value of dp dt occurs when the population is half of the carrying capacity. Time to the maximum rate of change is equal to that equation right there. So what kinds of things are we going to do? What types of things are we going to do? You're going to be given a logistic differential equation, and what do you think you're going to have to do with that? Solve it. Now here's the thing. This is what I'm telling you right from the beginning. Do you see all this work that you have to do to go from here all the way down to here? You don't have to do that every single time. You do not have to do that every single time. What do you think you get to do instead? Look what you have right here. You see this? What do you have instead? You have a formula. Effectively, do you have to remember how to integrate this by hand? No, you just get to remember the end goal and plug in the appropriate constants. So for example, when I give you a differential equation that is in the logistic model, can you identify L? Yes. Can you identify P? Hopefully. And can you identify the rest? Absolutely, hopefully. And therefore you can write the solution. You can write the solution. So you understand what I'm saying here? This is the example. Let's look at number 1 here. Let's look at number 1. 0.5p times 1 minus p over 2800. If we're going to write the general solution, we're not going to separate and integrate. Although you could. It's not impossible. Instead, you're going to use that formula. So what do you have to identify first, do you think? Well, go back up because I put it all the way back up here. Where was it? Oh, it's this right here. So if we take this right here, if we take this right there, and we put it down here next to this equation, let's put it all the way down. Let's put it right, we'll put it right here. Probably gonna cut something off, but that's okay. Look at that, we'll make it smaller. And make it the wrong shape. Okay, let's try it over here. There we go. It's not getting smaller. There we go. So if we use that generalized form, could we identify our K, our P, and our L values? Sure, well, P is in there. The function is in terms of P. So there's P, right? So what's our K value? K is equal to 0.05. And does this form match that form? Is it in the right form? Yeah, sometimes it's not going to be. A common thing they're going to throw at you is they're going to change it a little bit, and you have to do like a little bit of factoring. So do you see how there's a 1 right here? Is there a 1 also right here? Yes. So what is the L value? 2800. So we have the K value, and we have the L value, so the carrying capacity is 2800. Can we write the general solution? Yeah, we sure can. So look, over here, we get to this, right? Remember how we got to that? L is a constant because it's the carrying capacity. So if we wanted to isolate P on this, if we want to isolate P, what does P equal? 1 plus what? E to the what? So what do we have in this one we're working on? We have the K value and we have the L value. So what can we plug in? Oh, there it is. You see that, everybody? So we know that P is equal to 2800 over 1 plus AE to the negative 0.05t. What's the one letter in there that we'd want to solve for? What's the one letter that's left? The A value is left. And the only thing you really need to remember is what does A equal? What does A equal? L minus the initial population over the initial population. So in order to solve for A, you would have to be given certain values. So does this state an initial population in this question right here? Does it state an initial population? It doesn't state one. So this is as specific as we can get right now. This is as specific as we can get without that initial population. That should make sense because when we integrate, how many integrals are there for a given function? How many integrals are there? We need an initial condition, right? So in this case, the initial condition is population not the initial population. Without that, we're not going to be able to solve for this constant. But if I were to give you an initial population, let's say 100, L is 2800 minus 100 over 100, so it would be 27. Does that kind of make sense, everybody? This represents all of the possible solutions, and to find A, we need an initial population. So why don't you find a piece of the board? Let's do the next one at the board. Let's do the next one at the board. I know it's Monday, and the first one, you have your values straight out there. You have your K value, and then you have your L value, right? This is the only thing you have to take care of in the second one. That's 25 over, was it one like this? Is it 10,000 or 100,000? 10,000? Wait, tens, hundreds, thousands, 10,000, 100,000. Right, okay. So, but then what does that equal? 1 over what? 4,000. Right? You good with that? So what does L turn out to be on this one? 4,000. Now, without an initial population, without a starting point, we don't know what the A value is. So for the time being, when you write these final answers, I like seeing this. I love people writing like P is equal to 4,000 over 1 plus, what was it? A e to the negative what? What is it? 0.68? 0.68? Yeah, 0.68 t. I like that. And then writing A is equal to what? L minus P naught over P naught. You don't know what it is, but you could figure it out. So you could plug in L right there. You know what L is, but you can't figure out what A is because you don't have a condition. You don't have a condition to work with. You do not have a condition to work with. Oh look, you guys agree with that work right there? Yay, you sure do. Okay, so try this one by yourself. You are now given enough information to actually solve for the complete differential. Hey, why do you have to factor? Yeah, it's not in the right form, is it? So what do you have? dt, what do you factor out? What should I factor out? 10p. Yeah, factor out 10p, because then it was 1 minus what? P over what? P over 2, right? Do you agree? Yeah. Why is that helpful, Ian? Walk me through it now. Walk me through the next one. Why is that helpful? Yeah, what do you now know? What does that tell us? Oh, it's frozen. I'm sorry. What does that tell us now?
We have our
what values do we have? Yeah, so we have our, is it K value? What value is it? What value? I'm sorry. K value? I just couldn't hear you. K is that? Yep. So we know our solution. Negative 10t. We're not quite done yet though, right? You guys have been finishing it up as A equals L minus what? P naught over P naught. Are you given something? Yeah. So can you do something with that now? Finish it up for me, everybody. Finish it up. What's that key fact about logistic curves? The steepest one halfway between, it's half of what? L, right? So what do you set that equal to? So this happens when, now this happens when what happens when P is equal to L over 2, right? Correct? But we know L, I'm just starting from the beginning, we know L is 2, so that happens when, so L is 2, so P is going to be equal to 1, correct? So where do we take this? Where do we plug that 1 in? We set it equal there, and what do we have? 1 is equal to 2 over 1 plus 3e to the negative 10t. What do you need to solve for? T. Do that for me now. Remember your log.